Previously, we extended the definition of velocity, acceleration, and displacement to 2 dimensions. And there made the observation that all the differentiations, which is that process of taking limits over ever smaller intervals, that we only operated on the x components and on the y components separately. There was no crosstalk whatsoever between the x and y components. So the deal is that when we're looking at motion in 2 dimensions, or in fact in 3 dimensions even, because this extends to that, we can treat the motion as mathematically as if it were 2 separate relations, 2 separate situations. One looking at the motion in x purely as one-dimensional motion, and looking at the motion in y purely as one-dimensional motion. And because nothing's changed with the relationships between the variables, between the position, velocity, and acceleration, both for the x component and for the y component, the net result of all of this is that we have now 2 gangs of 4. One for the x components and one for the y components. So now what I'm doing here is I am walling off the territory between what I'd like to call here the land of x. Oops. The land of x, and over here the land of y. And the important thing to know is that no information can travel back and forth between these with one exception. That exception is the time. So only the time can cross between the land of x and the land of y. So otherwise, anything that happens with the x coordinates stays in the land of x. Anything that happens with the y coordinates stays in the land of y, and only the time can go back and forth between these 2 lands. So I'm going to go ahead and do a few examples of how this sort of thing can work. And generally speaking, what you'll do is you'll choose your coordinate system so that the acceleration points in one of the directions, usually the y direction. And then we will have to separately do a gang of 4 selection procedure between the land of x and the land of y. Now what you'll find is that a lot of the times in one of the 2 lands, you'll be missing more than one variable. And if you're missing more than one variable, that means you don't have enough information yet. But you can go to the other land and solve for the time, because if you have more than one piece of information missing, one of the pieces missing will be the time. So you can go to the other land and solve for the time. I would say probably 95% of the time you would solve for the time in the land of y, and then have to send that information back to the land of x, but about 5% of the time it cuts the other way. So I think probably the best way to see this is just to go ahead and work a few examples of it. So we'll start by throwing a ball off of a cliff. So the cliff is really high, so that we don't have to worry about the ball actually hitting the ground. So here you are, and you go ahead and throw a ball, and let's say you throw the ball horizontally at 5 meters per second. So now the way we would write this is that the initial velocity is 5 meters per second I hat, and we could write plus 0 meters per second j hat, but I'm not going to bother here. So we can go ahead and write down what the x and the y components of the initial velocity are. So Vix will be plus 5 meters per second, and Viy will be 0 meters per second because we're going horizontally. Now, what we want to know is what is the speed, so just v, no vector, anything like that, at delta t equals 2 seconds. So we've been given our time here. Now, this may look initially like we don't have enough information. We don't really have much in the way of any position information. And it doesn't seem like we've got any acceleration information, except that we do. We can assume that we're throwing the ball on the Earth. And so if that's the case, then my acceleration will be minus 9.8 meters per second squared. And since it's pointing straight down, that would be j hat. So, or we can write it as a sub x equals 0 meters per second squared, because there is no, we look at this, we're accelerating straight down, there's no right and left to this, so the x component of the acceleration is going to be 0. And the y component of our acceleration will be minus 9.8 meters per second squared. All right, so we want to know what is the speed after 2 seconds. Well, when we do this kind of thing, we separately look at the land of x and the land of y. So I'm just marking off my lands of x and y here. And remember, the only information that can go in between them is the time. Well, we have the time. So in this case, we don't have to trade any information between the two lands. That will be for a later example. So here we go ahead and ask ourselves, what are we looking for? Well, part of our strategy is we want to know the final speed. In order to get this, we're going to need to know what v sub x final, sorry, v final here, and v final y are equal to. If I know that, then the game plan is I can use the Pythagorean theorem to get the final velocity. So let's go and take a look at the land of x. So in the land of x, I'm trying to solve for v final x. So that is being asked for. What's given is, well, we have v initial x is given. That's 5 meters per second. We know the x component of the acceleration is 0 meters per second squared. And we're given the elapsed time as 2 seconds. So what we're missing, So what we're missing is our x. So we use the equation that doesn't have an x in it. So that'll be v final x equals v initial x plus a sub x delta t. Now, like I've said, you never want to put in numbers right away, but the one exception to that is 0. So a sub x being 0 makes this whole term drop, and we get that in the that the final component of velocity in the x direction is just what we had to begin with, or 5 meters per second. And we'll say plus, so we remember it's going to the right. Okay, land of y is going to be the same kind of process. So v final y is something we're asking for with the idea that we'll put it all together to get the final speed. Now here we've been given that v initial x is 0 meters per second. A sub x is minus 9.8 meters per second squared, and that delta t is 2 seconds. So here again, what is neither asked for nor given is the final y coordinate. So we can say that we are missing y final. So then we can say that v final y equals v initial y plus a sub y delta t. V initial y is 0. So this will be minus 9.8 meters per second squared times 2 seconds to give us minus 19.6 meters per second, because 1 power of seconds cancels against 1 power of seconds there. So now to get my final speed. If I draw a vector of my final velocity, it's going to look something like that. And we can just go ahead and dot in. So this is my v final that I'm trying to find the magnitude of. So v final x we know is 5 meters per second, and that's positive because we're going rightish. And v final y is minus 19.6 meters per second. And we can use the Pythagorean theorem to put the two of those together. So v final will be equal to the square root of v final x squared plus v final y squared. So that will be the square root of 5 meters per second squared plus negative 19.6 meters per second squared. And since it's squared, the minus sign is going to go away, which is a good thing because we were interested in speeds. And if you punch this through your calculator, you'll get 20.2 meters per second. And this at least passes a little bit of a sanity check in that it's faster than the y component, which it should be because we also had an x component. And also because it's mostly down and only a little bit to the right. And we see that this is only a little bigger than that. That makes us feel even a little better. All right, let's try a slightly more challenging one. So now let's say we have a cliff again, and we're going to throw a ball off of it again. But this time, we're going to say that my cliff is 100 meters high. And I've got a bucket over here, 50 meters away. And what I want to do is I want to throw the ball so it lands in the bucket. And so I'll go ahead and throw it purely horizontally. So what I want to know is how fast should I be throwing it? Okay, let's go ahead and here we'll want to pick a coordinate system. And well, this is, I guess, is a sensible choice as any. We'll put the origin right here. So this is going to make x final equal to plus 50 meters, y final equal to 0 meters. And on the initial side here, this is going to make x initial 0 meters and y initial plus 100 meters. We also know that we're throwing this on the Earth, so we can go ahead and draw in our acceleration as being minus 9.8 meters per second squared times j hat. So this will let me write that a sub x is equal to 0 meters per second squared, and a sub y is equal to negative 9.8 meters per second squared. All right, so the trick here is I want to figure out how fast I can throw this so that it will land in the bucket. So initially we can go ahead and just divide up our land of x and our land of y separately here. And let's start to think about what we know. So in the land of x, we know that we know x initial and x final. X initial is 0 meters, x final is plus 50 meters. We know that a sub x is equal to 0 meters per second squared. And what we're going to want is v initial x. We know that, so here we know that v initial x is the thing we're looking for. We do know that v initial y is 0, because we're throwing this horizontally. So if I can find v initial x, I find my initial speed and I'm good to go. But I've got a problem here. I do not know the final velocity. So I do not know v final x. And I do not, well, I do know, well actually I do know it, but it won't be helpful. And I also don't know the time of flight. Now, you could go ahead and say we do know what v final x is after all, because the x component of acceleration is 0, right? So then you might be tempted, so this is going to be a don't try this at home, kids kind of moment, but I just want to give us a cautionary tale here, so I'll draw this in gray. You might be tempted to say, well, since I really do in my heart of hearts know that v final x, whatever it is what v initial x is, maybe that gets me somewhere, but it doesn't really. Because we can say, well, if we're missing delta t, we can say v final x squared equals v initial x squared plus 2a sub x delta x. And you go ahead and realize that a sub x is 0, and we're just back to what we had before, that v final x equals v initial x, which we knew, but it doesn't get us anywhere. So we're kind of left with, okay, what else can we do here? Well, we can go to the land of y and look for delta t. So we'll go ahead and just put an x through this as a bad idea. And we'll go over here to the land of y and write down what we know. We know y initial is plus 100 meters. We know that y final is equal to 0 meters. We know that a sub y is minus 9.8 meters per second squared. And we want to know what delta t is with the idea of sending that information over to the land of x. Well, that works out okay then, because what we're missing, and we also know that v initial y is equal to 0. So what we're missing here is just purely v final y. So now we can go ahead and use the missing v final to solve for that. So we'll go ahead and write that y final is equal to y initial plus v initial y delta t plus 1/2 ay delta t squared. And again, I'm always strictly opposed to putting in zeros or any number other than 0, but putting in 0 itself is okay. So y final is 0, I'll put that in there, and since v initial y is 0, that makes that term 0. All right, so now it's just doing algebra to rearrange to solve for the time of flight. So I can subtract y initial from both sides, so I'll have 1/2 ay delta t squared equals minus y initial. I can times through by 2 and divide by ay. So delta t squared equals minus 2y initial over ay. So then finally, to get my time of flight, that I will send back over to the land of x, I'll just take the square root. So delta t will be equal to the square root of negative 2y initial over ay. Now, when you look at this, you might be worried because it looks like I'm taking the square root of a negative number here, but this actually isn't a problem. Why is that? Pause the video and get back with me. Okay, so the reason it's not a problem is because we know that y initial is positive, but a sub y is negative. So with a minus sign here and this number being negative, that's actually going to make the whole thing under the radical a positive number. So I'll be taking the square root of a positive number, and it's all good. So now with that, we can go ahead and send that information back over into the land of x. So we now know that delta t is the square root of minus 2 y initial over a sub y. So now with that, we can go ahead and use the missing v final, because remember, we know that v final is v initial, but we don't know what it is. So probably the best approach here is to use missing v final, although there are other ways to tackle this one. But we'll use missing v final. So we'll have that x final equals x initial plus v initial x delta t, which we now know, plus 1/2 a sub x delta t squared. A sub x is 0, x initial is 0. So I get that v initial x, which is the v that I want, because remember we're throwing this purely horizontally, will be equal to, I'll divide both sides through by delta t, there'll be x final over delta t. And with the delta t that I brought in from the land of y, that's x final over the square root of minus 2y initial over ay. Clean that up just a bit. We get that that is the same thing as x final times the square root of minus ay over 2y initial. Okay, now we can go ahead and put in our numbers. Notice I held off on putting the numbers to the bitter end. Since the problem did not ask for the time of flight, just simply asked how fast should I throw the ball, we don't need to know the time of flight. If I were to solve for the time of flight and then stick it into the next step, that would create some accumulated round-off errors that I would like to avoid. So I'll keep this purely symbolically until I need numbers, and now I do. So x final is 50 meters. This will be times the square root of minus. Then a sub y itself is minus 9.8 meters per second squared over 2 times 100 meters. All right, so that works out to be 11.1 meters per second. Okay, good. The units check. What about the reasonableness of the value? Well, rough rule of thumb, meters per second going to miles per hour is a little more than double. In fact, in this case, 11.1 meters per second is about 25 miles an hour. A professional baseball pitcher can throw a fastball at more than 100 miles an hour. So thinking that a person could, with effort, throw a ball at 25 miles an hour seems reasonable. So looks like we're doing okay. All right. Let's do one more example. This is probably pretty close to as complicated an example as it gets. I could make it a little more complicated, and I'll explain how. Of course, as you can probably figure out from the channel name, I am of the opinion that the most awesome and extreme of all possible sports is, of course, target archery. But within archery, there is a discipline known as flight shooting. Flight shooting is where you just literally shoot for distance. So let's go ahead and do an example of that here. So let's say we have an archer. So of course an archer would be wearing a hat in order to protect them from the sun. And I'm going to make this slightly less realistic by having our arrow be at the ground level. Obviously you can't really do that, but it would be the problem suddenly becomes a whole lot harder if I don't make the initial height 0. So we'll say that y initial equals 0 meters. So in this example here, let's go ahead and say that our archer shoots the arrow at an angle of 30 degrees above the horizontal. While we're at it, we will neglect air resistance, which in reality you can't do. And so what we just want to know is, well, okay, you know, the name of the game is maximum distance here. How far did the arrow travel? So we're really asking for x final because we can choose our initial location to be 0 meters. And of course we realize that at the end of this, where it lands, y final is also going to be 0 meters. Well, what else do we know? We can be given, I'll give you the velocity of the initial speed of the arrow, I should say. Let me go ahead and draw that in blue here. The initial speed of the arrow, or initial velocity of the arrow, is 60 meters per second, and we're launching at 30 degrees above the horizontal. So one of the things we'll eventually have to do is we'll have to think about the x and y components to this, because in order to, v initial y, because in order to separate this into land of x and land of y, I need to break the components up. Well, this angle here is the adjacent, so we'll just go ahead and note right now that v initial x, since this is the adjacent, will be equal to v initial cosine theta, and v initial y will be equal to v initial sine theta. And we got that from doing SOHCAHTOA. If that seems a little unfamiliar, pause the video, convince yourself that that works out. And again, we're playing archery on Earth, so the acceleration will be minus 9.8 meters per second squared times j hat. So we're going to say that a sub x is equal to 0 meters per second squared. A sub y is equal to minus 9.8 meters per second squared. All right, so I think we're doing pretty good here. Now, let's go ahead and start writing down our land of x and our land of y and figure out what we've got. So we'll just start with the land of x. And we know that v initial x is equal to v initial, which we know it's 60 meters per second, but I'm going to be lazy about putting it in right away. Cosine theta, and we know theta, that's 30 degrees. Same deal, I'm going to be lazy putting that in right away just because I want to stick all the numbers in the calculator at the end and no sooner. But anyway, this is a thing we know. We know that a sub x is equal to 0 meters per second squared. We're being asked to find x final. And let's see, what else do we know? We do not know the time of flight. And it seems, and again here, you might think, well, you know what? I really do kind of know the final velocity because a sub x is 0 meters per second squared. I really do, deep in my innermost heart, know the final velocity. We can observe that that's equal to v final x. But again, this is going to be one of those cases where it's not going to help us, because you might think that you can get away with going ahead and trying the missing delta t, since it seems like you've got everything else. But if you were to try that, what have you got? You've got v final x squared equals v initial x squared plus 2a sub x delta x, where delta x here is x final minus x initial. So that's all looking good, right? But here's the problem, is that these are going to cancel. So you got 0 there, and that's going to equal 2 a sub x delta x. Still looking good, but the problem is a sub x is 0. So you get yourself a divide by 0 problem. So once again, that approach isn't going to work. So we're stuck with what we were suspecting we'd have to do all along, which is go over to the land of y. And here now we are going to want to solve for the time of flight, with the strategy being that we will take that time of flight that we solved for, stick that back over into the land of x, and we'll be able to use the missing v equation to solve for the distance traveled. All right, so with that as a strategy, let's start putting together what we know in the land of y. We know that y initial equals y final equals 0 meters. We know that a sub y is minus 9.8 meters per second squared, and we know that v initial y is equal to v initial sine theta. And again, we know that v initial is 60 meters per second. We know that theta is 30 degrees, but let's not stick those numbers in right away because, again, we're not asked for the time of flight. We're simply asked for how far is this traveling. So we're better off leaving the time of flight as an algebraic expression to substitute into the land of x in order to minimize accumulated round-off errors with our calculators. All right, so if we go ahead and look at this, what we are missing is vy final. You could reason through that by the symmetry of the situation that vy final is minus vy initial, and you won't get any divide by zeros this time, so that is an alternate route to solving it, but let's just go with missing vy final here. So the missing vy final says y final equals y initial plus v initial y delta t plus 1/2 a sub y delta t squared. Again, I'm not a fan of putting in numbers with the exception of 0. Now, y final and y initial are both 0. So, okay, that's looking promising. And we can solve, so what are we left with? We've got 0 equals. Now, each of these terms left here has at least 1 power of delta t in it. So to solve this kind of a thing, we're going to factor out a delta t. So this will be delta t times the quantity v initial y plus 1/2 ay delta t. Okay. So remember the idea here is that we have 2 roots to the equation. We have the root, either this is 0 or that is 0. Both of these are possibilities because either way would make the product 0. Well, if the pink squiggles is 0, that gives us the root delta t equals 0, which is legit. It's asking where is the height 0, and the height is 0 when we first shot the arrow because of my unrealistic assumption that it was being shot at ground level and not about a meter above the ground, which is what would be more typical. So it's a valid answer, but it's not the one we want because we want the time, because we want to know the other time it hit y equals 0, which is when it landed. So we will discard that root and instead look at the case where 0 equals v initial y plus 1/2 a sub y delta t. Well, we can rearrange that to get that delta t is minus 2v initial y over a sub y. And this looks like this could be problematic because it doesn't look like the time is negative. But again, it's okay because a sub y is negative. So this is actually going to be a positive number, so we're all good. So we've found our expression for the time of flight, and we can now take that information and transfer it back over to the land of x. So we'll have that delta t is minus 2 v initial y over a sub y. Now with that, we can go ahead and there there's more than one way to do this one, but let's just go ahead and use the missing Vx final. So that one's going to be x final equals x initial plus v initial x delta t plus 1/2 a sub x delta t squared. X initial is 0, so we can put that 0 in right away. And a sub x is 0, so we can put that 0 in right away as well, making that third term drop. So we get that x final will be v initial x times minus 2 v initial y over ay. We can clean that up a little bit. Minus 2 v initial x v initial y over ay. And we can put in our algebraic expressions for that. This will be minus 2 v initial x was v initial cosine theta. V initial y was v initial sine theta over a sub y. Finally, we can clean that up just a little bit more to get that x final equals minus 2 v initial squared sine theta cosine theta over a sub y. Now let's go ahead and put in our numbers. So this will be minus 2 times 60 meters per second squared sine of 30 cosine of 30 over minus 9.8 meters per second squared. So those minus signs will cancel. That's good. And we get finally that x final is plus 318 meters. All right. So the units check. That's good. Does the answer make sense? Well, if you're on top of the ins and outs of flight archery, you know that the world record is 1,222.01 meters. So this isn't exactly a spectacular attempt, but it seems reasonable. You also know that in the Olympics, you shoot at a target at 70 meters. So it kind of makes sense that if you're just flinging for distance, that most archers could probably get it out a few hundred meters, and you would be right. So that does seem pretty plausible there. Now, the sharp-eyed among you may have noticed that I walked right up to within a gnat's eyelash of a thing called the range equation, but didn't actually give it to you. And there is a really good reason for that. If in a previous lifetime you have encountered the range equation, I would actually strongly urge you to forget it. There's a really good reason for that, and that is, what if I had told you that the initial height wasn't 0? The range equation, if you've ever run across it, is very specific to the idea that the initial and the final heights are 0. And it's just so easy to tweak the problem so that that doesn't work, that I am a big fan of not ever using the range equation. So that's why even though I walked right up to it, I didn't give it to you. Now, if you don't know what the range equation is, I would actually urge you to stay ignorant of that, at least for now, because you'll find that it'll serve you a little better in the long run. Alrighty, so in the next video, we will go ahead and loop back a bit to the idea of relative velocity, which kind of ties in with what we were doing with this flight shooting problem. So we'll go ahead and catch you over there.